Hi everyone, I'm really sorry that I'm not there with you today, but I am glad that we can have this video to help you as you become familiar with calculating water potential. Looking at this table, I want you to notice that the majority of this information is straight off of your AP biology equation sheet. The things that I have highlighted in yellow is information that I have found is helpful to have, but is not on your sheet. So I would include some of this information on my one pager if it was me, and then kind of squirrel that away so that when you are studying for your AP test, you can find that information. Water potential is just the tendency of water to move from one area to another. And as we saw in the lab, the Orbeez lab, water has a tendency to move in the direction of the higher concentration of solutes. Now, the higher the concentration of the solutes in a solution, in a cell, that is the, when we calculate water potential, it will have a more, my pen stopped working, let's try that again. It will have a more negative calculated water potential value, and that value is going to end up being hypertonic, so there's some of that language coming back. And what that also means is that the lesser concentration or the lower concentration of solutes is going to give us a less negative water potential value. Whenever I say less negative, more negative, let's keep in mind a number line. Let's kind of go back to a number line. And if we were to have some negative values, we need to remember that the one closer to 0 is going to actually be the larger value, even though the number itself is smaller. Now, the other thing to recognize here is that the movement of water is going to be from the high water potential to the low water potential. So water will move from high water potential to low water potential, because you're going to have some questions on this sheet that's asking you, now that you've calculated your different water potential or your pressure potential or solute potential, whatever the questions are asking you, it's going to ask you to, what does that mean for water and how it moves? Is it going into the cell? Is it coming out of the cell into the solution? And that's going to be based on that value. The high, it's going to go from high to low. Here's our first cell we're going to work together on. I have a solution in a beaker that has a solute potential of negative 0.5, and then I have a cell with a solute potential of negative 0.9 that has been placed in that beaker. I want to know what the pressure potential of that flaccid cell is before it was placed in the beaker. And since it's flaccid actually means like limp or wimpy, so there is no water in that cell right now, that means that a flaccid cell actually will always have, I'm thinking more than faster than I'm talking, will always have a pressure potential that's equal to 0. Okay, so anytime it's asking for pressure potential, there's nothing in there, so there's no pressure being exerted on the walls of the cell. Next, we want to know about water potential of the cell. All right, so now we can do a little bit of math. One thing I have noticed that helps a lot is if when I am doing these problems, I identify whether I'm solving it for the cell or the solution. That has really changed my ability to do these this year. So using the formula straight off of the sheet, I have the pressure potential of the cell plus the solute potential of the cell. And then I look up and I know that the YP, remember it was a flaccid cell, so that's 0. And the solute potential was up here in my problem. That was negative 0.9. And whenever I do that math, it is really hard to write on these. I should do this more often so that I get good practice and then my writing won't stink so bad. And circle your answers. So when you do the math, that's what we get for the water potential of that cell. Next, we're actually asking about the potential of the solution. So we're going to use that same equation, but now we're focused on the solution. So that's going to equal the water or pressure potential of the solution plus the solute potential of the solution. Now, back on that table, it tells you that the pressure potential of an open beaker is 0. So we know that this is going to be 0. And then in our problem itself, it tells you that the solution has a solute potential of negative 0.5. We do that math and we see that the water potential of the solution is going to be equal to negative 0.5, and then don't forget your units. Okay, moving on, we have how will the water move? And we've got to circle and identify, is it going to move into the cell or out of the cell? And then how do we know? Like, what's our justification? So we need to recognize that the movement of water is going to be from high to low. So remember, we have the high potential to the low water potential. And when we're looking at our math that we did, our calculations, the solution is actually going to be greater than the cell. So I could look at that visually because I'm a visual person here. And I got a beaker with some sucrose solution in there. I have a cell. Remember, our cell was the negative 0.9 and our solution is the negative 0.5. And what that means is that the movement of that water is going to be into the cell. So into the cell. And that means that the cell is actually hypertonic because it has more solution, more solute, The pressure potential. So now we're moving to this last piece of the plant cell when it's in equilibrium. You guys, that's going to be important, this equilibrium, because at equilibrium, whatever the water potential of the cell is, that's what the water potential of the solution and vice versa, because it's in dynamic equilibrium. So there's no net change and one will equal the other. So we know we can just solve, we would just start with one. We'll just start with water potential of the solution, and that is going to be equal to the pressure potential of the cell plus the pressure or the solute solution of the cell. So that's the equation I would use. And then I can just plug in those numbers that I calculated earlier for those. I do apologize for my writing. Now, this is very basic algebra. So since I have a negative on that side, we're going to add it to get to 0, but I have to add it to both sides. And then that means that I'm going to end up with an 0.4. So my pen stopped working again. So my pressure potential of the cell is going to be equal to 0.4. Don't forget to circle your answer. And remember, that's because at equilibrium, the water potential of the cell is the water potential of the solution. Okay, as you saw in that last problem, it's a little bit of plug and play algebra. Here is the next example. I really just wanted to set this up. That's what I did in class today. So we see that it's in equilibrium again. So I know that that means that whatever I have for the cell is going to be the same. The water potential for the cell is the same as the water potential of the solution. Now, notice that I have a lot more information provided here. I have a cell in equilibrium with its surroundings at 30 degrees Celsius. You guys, that's T for temperature, but in our table, it tells you that when we have temperature, we have to take that, whatever that temperature given is, and add it to 273 because we need to convert it into kelvins for it to work in the equation. All right, we have molarity. Molarity is C, and that is 0.5. We're going to calculate the solute potential. So we're looking to the right side of that equation sheet, and we see that the solute potential, and it's of the solution, is going to be equal to that negative ICRT. Okay, so we're going to go back up here, and we see, oh, it's sucrose, and that means I is going to be equal to 1. So when we plug this in, we've got our negative, we've got the I. C was the molarity at 0.5. R is a constant, so it's given to you on the equation sheet. You just need to look at the units given in the problem so that you can match them up and use the appropriate conversion and constant. I should say the constant. Okay, and then we have our temperature that we calculated earlier at 303. When you multiply all of those across, we see that our solution potential, solute potential of the solution is a negative 12.6, and the units for that is bars. Well, I said I was just going to set it up, but I did a little bit more. So I guess if you're still listening to this, you are getting a little bit more information than I originally planned. That's fine. What is the water potential of the solution? So we got to identify those things. Are we talking about solutions or cells? So water potential, remember, of the solution is going to equal the pressure potential of the solution plus the solute potential of the solution. All right, so we have the pressure potential of the solution. It's in a beaker. So I know it doesn't say that here, so this is an important thing to note. Unless it tells you it is in a sealed, vacuum-sealed container, which very rarely will you see a problem that says that, your pressure potential for a solution is always going to be assumed to be 0. So we'll go ahead and record that. And then in our problem that we just calculated in A, we know that the solute potential is a negative 12.6. Do that math, and we have negative 12.6 bars for our water potential of the solution. Down here, we're doing water potential of the cell. Now, you guys, this is where we're going to recognize that my pen stopped working again. Okay, here's where we're going to recognize that the water potential, or the water potential of the cell is equal to the water potential of the solution, because it's in equilibrium, plus the water potential of the, oh, that is not water potential, okay, let's try that again. Plus the solute potential of the solution. So the cell equals the solution. So then we can just plug in all of our numbers. We have that pressure potential again of the solution being 0. And we had calculated in that previous problem the negative 12.6 of the solute potential. So we add all that together, and the water potential of the cell is going to be negative 12.6. Okay, and so that's 2 problems. If we wanted to see what that looked like, I didn't make that big enough. Let's try that again. We have a negative 12.6 there, a negative 12.6 here. So what we're going to see is water going in at the same rate as water's coming out. Equilibrium. That's what that looks like. Okay, I am done. I'm going to leave you with the rest of these problems to do on your own. However, my answer key is posted to Canvas. Please, please, please do me a solid and try to do the calculations yourself before looking at the answer key. And that way we can confirm our thinking as opposed to just copying things down. All right, you guys, I'll miss you, and I'll see you in a couple of days. Bye-bye.